Hello, thanks for watching. In this video, I'm going to demonstrate how we use a ruler and some colored pens or pencils to do what's called ray diagrams for concave mirrors. So, just a reminder that spherical mirrors, which is the model that we're going to be using, can be either concave or convex. The ones that we're going to be doing here today, for this video at least, are the concave ones. So they cave in the middle is how I describe it. It's like the bowl of a spoon, but when you flip the spoon over and look at kind of the underside of it, that's the convex side. Okay. So what we want to do is imagine we put something in front of one of these concave mirrors, and the question is, when we look into the mirror from a distance away, what will the image look like? Obviously, we'll be able to see the real object, but what will the image look like as well? And what in the physics classroom, they have a scheme where they use what they call the LOST kind of acronym to describe an image. So you see it here on the screen. We want to describe its location, like around where does this image appear. What is its orientation? Is it flipped or not? What is the size? Is it bigger or is it smaller? And what type of image is it? It can be virtual, like a mirage, or it can be real. And real means something you could actually put on a piece of paper and touch with your hands. So the scheme I'm going to be using is kind of summarized on this page here. So there's kind of two approaches to this. There's the drawing approach, which is what I'm going to show you here, and then there's the math approach. Both will give you the same, I guess, result or answer, and so I'm going to have you do both and make sure that your answers come out consistent with the other. And then there's also a third method. Since we have access to the simulator on Physics Classroom, we'll put it into the little virtual optics bench, set it up, and make sure that what it shows us looks just like the results that we got. So it's almost like a triple check. Okay. So for the math, we end up using kind of the top of this page and the equations at the bottom. But for the diagrams, we're going to use the part here in the middle. I also made this to be useful for lenses, because we're going to be doing lenses in a different unit. But we'll ignore that for now. Also note here that I tried to make this as compact as I could. So these little, what I call the rules for how to draw these light rays, are good for both concave mirrors, and if you add the words in parentheses, they're going to work for the convex mirror as well. Okay? And all of these rules, just keep in mind, are based on the law of reflection. That very familiar, kind of in your bones, understanding that when things hit off of a boundary, that they will reflect off that boundary at the same angle. So this is the basis of the game of pool or billiards, basketball, any racket sport. And so it's a little harder to see with these spherical kinds of mirrors compared to the plane mirrors that we used before. But trust me that all these rules are based on that very fact. I'll try to describe that as I go through the drawings. So essentially what we're doing is we're imagining, so here's in this first example, you're just going to draw along with me here. Here's an object. We always use arrows for our objects because they're so easy to draw. You don't have to be an artist. And we've placed it in front of this concave mirror. Now, it's not very curved. I curved it just a little bit. And there's a couple of things that we want to label first. First of all, here, of course, is the mirror. When I did plane mirrors, I called, there's like a mirror plane. This doesn't really have a mirror plane because it's curved. But every curved mirror has a focal point. That focal point is kind of defined as the point through which all the reflections will go if the rays, the incident rays, come in perfectly parallel to this line here. So let me define what this line here is. This line is called the principal axis. I label it PA. And it's essentially like if you could imagine taking this mirror and turning it into the entire sphere. We're just seeing a little section of the sphere here. Think, a basketball that has a mirrored surface on it on the inside. That would be a spherical mirror. And we're seeing a little subsection of this. Well, this line here is like a diameter across the entire basketball. Okay, so it goes right through the middle of the ball, and it goes through, one part of the ball itself, the surface. That's the principal axis. So that focal point is the point where if we could imagine shining light on this mirror from far, far away, all the light that comes in parallel to this principal axis will reflect through this focal point. That's why it's called a focal point. You'll also hear it called a focus. So it's also important to know that the center of curvature, the center of this imaginary sphere, is also along the principal axis and twice as far from the mirror as the focal point is. So because I put a grid here, we can count, we always count our squares from where the principal axis is. So 1, 2, 3, 4, 5. 5 is what we call the focal length. It's how far from the mirror the focal point is. And so 5 more, 1, 2, 3, 4, 5, that is what we would label as C, the center of curvature. Okay? So again, imagine this entire sphere. Here's the center. Halfway between the center of the ball and the ball itself would be this focal point. Okay, so here's this object, and it's being illuminated by something, maybe some room lights or the sun, and all this light is reflecting off of it and going every which direction. Some of those rays are going to go in a direction where they will hit this mirror. We're going to pick a select few of them and show how they will reflect off of the mirror. Because geometry, and I'm not going to get into the background of all the geometry, but I think what I'm going to do here will kind of make sense when you see it. If you can imagine throwing a ball at like a curved wall or something and picturing how it would reflect off of there or bounce, this is going to make perfect sense. So those few predictable rules are what we have here under these rules for drawing ray diagrams. Okay, so the first two, incident rays, those are the rays that are going towards the mirror from our object. If they're parallel to the principal axis, they will reflect through the focal point. Again, that's how we define focal point. So I'm going to use my red pen here and a ruler. Please use a ruler for this. And I'm going to show that particular ray. So again, I'm going to try to find the image of the whole arrow, but I'm going to do it by finding where the arrow head is. I'll show you why that's actually the best place to use. So if a ray comes from, again, some source of light, happens to hit the arrowhead, and heads directly towards the mirror. So I put a little arrow like this. That shows me that that's an incident ray. The reflection will go right down through this focal point. So we reflect off the mirror. I like a clear ruler like this because it makes it really easy to find, everything. That is what that ray would do. So if you can kind of imagine my ruler here is kind of like the surface of the mirror right there. Like if I turned that part of the mirror into a plane mirror, that's pretty much how it would be bent. And this kind of makes sense for the law of reflection. Remember, the law of reflection says if I imagine a normal line coming directly out of this ruler here, that the reflection will be on the other side of the normal line at the exact same angle as the incident ray. That's the law of reflection. Now we're going to draw a second one. The incident rays that go through the focal point will reflect parallel to the principal axis. Okay, so let's use a different color here. Get some green. So now I'm talking about the ray that as it approaches the mirror heads through that focal point. So I'm going to draw the arrow in this direction. Again, show with a little directional arrow that this is an incident ray. That way we can tell like what's going towards the mirror and what's coming away from the mirror. And so remember this sort of reciprocity rule that, if I know that this is how a ball is going to bounce off of a curved wall like this, it doesn't matter which direction I'm going towards the wall. If I go this way, it bounces this way. But if I go this way, it bounces that way. It's got to be the same angle on either side of the normal anyway. So I'm making some extra marks on this by mistake. So I'm going to draw a reflection that is parallel to the principal axis. Like that. These grid lines really help with that. Now, please don't try to freehand this. This is just too rough to try to do without something like a straight edge. Now, at this point, you got to remember our eye is back here somewhere looking at the mirror and seeing all of these rays that will eventually hit the eye. We're only drawing a select few of them. There are, bajillions of them. Wherever all those rays, the line of sight, meets, that is the location of the image. We actually just found it right here. But I want to draw another ray anyway, because there's times where these are difficult to draw. So here's a couple more that we could use. Incident rays that go through the center will reflect directly back on themselves. So I'm going to use, I've got a brown marker here. Now this gets a little bit hokey because if the ray leaves the arrowhead and goes through the center of curvature and then goes this way, it looks like, well, it's not going to hit the mirror. You got to imagine the mirror kind of extends a little bit in order to make sense of this. So there's the ray that's going towards the mirror. But here's something you learned in geometry, which you probably don't remember. But a radius to a sphere is actually perpendicular to the sphere right there. In other words, it is its own normal line. So this ray hits on the normal line, and I know I didn't draw it that way, but like if I could extend that mirror, it would kind of be like that. And so it reflects directly back on itself, like if you throw something directly at a wall. So here comes the reflection back. And notice, if this eventually hit our eye, it would seem to be coming. Now, if we have multiple people looking at this, maybe somebody's looking this direction and somebody else is looking this direction. They all have to see the same image. The image doesn't move based on who's seeing it. All these lines of sight go back to this one point right here. Now, I do have a fourth one here. Again, this is overkill. You really only need two, but I'd like you to know all four. Incident rays that hit the middle of the mirror reflect symmetrically on the other side of the principal axis. Okay, here's what I mean by that. Well, I need another color. I'll use my black for this. If we hit the exact center of the mirror, right where the principal axis is, we will reflect at exactly the same angle. Now, I think for a lot of people, this one is the easiest one to imagine because it looks like it's hitting the flat part of the mirror right there. Okay? Technically, on a sphere, nothing's flat. But hitting like that is just like hitting a plane mirror, and so it's going to bounce off at the same angle. For this one, what I do is I just count squares. We're not going to use a protractor for this. So if this started, you see where this is? It's 1, 2, 3, 4, 5, 6, 7 squares up above the principal axis. Then the reflection will be 7 below. 5, 6, 7. Right there is where the reflection has to go. So I'm going to draw it going through that point as it leaves the mirror. So here's the reflection that way. And look again, right through that image location. So we have found the intersection of these. Again, it only takes two to intersect. We have found the location of where the image of the arrowhead is. And then the last point, number 5, any object on the principal axis will have its image on the principal axis. Well, what has the object on the principal axis is the tail of the arrow. I always put the tail of the arrow on the principal axis when I do my problems. It makes life easier for you. So that means that the tail of the arrow will be somewhere on here as well. And here's what I'm going to tell you. It's always right above or below where the arrowhead is. The arrow image is not going to be like rotated or anything. So right there. And so we're going to draw this image. It's right there. Here's the arrowhead. It's very important to draw an arrow. Now, it's a little hard to see because there's a lot of stuff going on there. So I sometimes label this I know it's a little small, but that little arrow right there, that's the image. So imagine you're back here looking at this. You see the real arrow in front of you, but you also see this little image a little further away. And using the lost method, oh, I don't want to do that there. L-O-S-T. This location, approximately, if we count squares, 1, 2, 3, 4, 5, 6, 7 and a half-ish. Now, these can be estimated because your drawings are going to be a little bit off. 7.5. We're using centimeters. We'll pretend these are centimeters. The orientation can be upright or inverted. Notice in this case the arrowhead is now pointing down, so this is inverted. The size of the image is just how tall it is. We're going to count the squares again. So we started with an arrow that was 7 tall, but this is 1, 2, 3, about 3.5, 3.5 centimeters. And here's a convention. I'll show you these sign conventions. If your image height, if your image is inverted, we always call the image height negative. It sounds kind of weird. It's like if you were standing on your head, you'd suddenly have a negative height. That's not like a real thing. That's what we call a convention. This is just something that makes the math work out. So it's negative 3.5. We also often describe the magnification. That means how tall is the image compared to the initial or the original object. In this case, 3.5 compared to 7, it would be a magnification of -1/2. So it's half as big and flipped. Okay, you'll see that used sometimes. I don't generally use that. Type. Is this real or is it virtual? Well, here's how this works. This is the first time we've seen this because in our plane mirrors, they were all virtual. They were on the wrong side of the mirror. We couldn't actually go up and touch them. But this is all on the real side of the mirror, and so this is a real image. I will tell you, when you have a mirror like this, every real image will be inverted. Every inverted image is real. So that's kind of a giveaway. And when we do this in class, we'll be able to put this real image on our hand if we want to. You can't feel it because it's light, but you can see it for sure. Your eye will not know the difference between a real or virtual image. It's like a mirage, you know. It just looks real to the person looking at it, but there's definitely a difference when you try to put it on your hand. Okay, so there's an example of how you do a ray diagram. Again, a little bit of overkill. I won't do 4 every time. And we found the location, or we found everything, all 4 features of this. Okay? All right, so I'm going to pause here for a second, and then we will do the second one, and I'll show you how this can have a little variety. Okay, so if you look at the third example, which is this one here, there's something unique about this, which is why I want to show it a little separately. But I'm going to go a lot faster through this because you've already seen most of the important basics. So what we did is we moved the object very, very close to the concave mirror. Okay, and a really interesting thing happens. Again, we're talking about, like, if you were to look into a mirror like a spoon, and pull it up really, really close, things change. And some of you have had that experience. So going through again, these rays in order. I'll do the first one in red. This rule said, I'm not going to show you again, but if a ray comes in and hits the mirror and is heading parallel to the principal axis, that short little distance there, the reflection will always go through the focal point. And that's how we define focal point. So from here, we reflect down through the focal point. I picked about the cruddiest ruler I could find here. You can't tell, but it's all chopped up. It's like somebody chewed on it. Okay, and the second rule says that if a ray is heading towards the mirror and goes through the focal point on the way to the mirror, that it will come off parallel to the principal axis. But that gets a little goofy on this one because if a ray, like from the sun or from a room light, bounces off this and heads through the focal point, well, it'll never actually go to the mirror. It's going the wrong direction. So here's how I modified this. Incident rays that would go through the focal point will reflect parallel to the principal axis. So, imagine a ray comes off of this and is heading towards the mirror in a direction that is coming from the focal point. So, what we have to do is put the ruler down on the focal point and on the tip of the arrow. So, instead of, you could, I guess, draw the ray like this. But what I always do is I start it at the arrowhead. All my incident rays I start at the actual object, the arrowhead. But it is coming in a direction that is from the focal point. Okay, so that's really important. I'm not just picking any old random line here. Geometry is pretty precise. This is all based on geometry and the law of reflection. So now we're hitting. Again, imagine we hit a plane mirror like that. It's going to bounce. And this is the one that reflects off parallel to the principal axis. You might call it, straight, but these are all technically straight. There's the reflection for that ray. You notice something odd about this. Because what we're looking for, here again, here's our eye. Our eye is over here. Somebody else's eye is over here. We're all looking at these rays along our lines of sight. And the eyes just all follow it back. And wherever all these rays are coming from, must be the location of the image. But if you follow these back, they're on the wrong side of the mirror, or what I like to call the virtual side of the mirror. So you have to do this when your object is very close to the focal point. You will always have to extend the rays to the other side of the mirror. Now, none of this that I'm going to do from here on is real stuff. This is all virtual. And anytime I do virtual things with mirrors or anything, I draw it dashed, okay? So I don't lose sight of the fact that this is all just kind of what our eye is doing subconsciously, but it's not real. It's like a mirage, or an optical illusion, or I jokingly call it a Fig Newton of your imagination. If you've never heard that before. The proper phrase is figment of your imagination, but in my goofiness I say Fig Newton. Right there, that is where the image is, because that's where all these people see these rays coming from. I'm going to do one more. I could do, yeah, I'll do that third one. The one that goes through the center of curvature is the one that also reflects back on itself. That's actually a really easy one to draw. Now, where's the center of curvature? Well, again, it's 1, 2, 3, 4, 5. It's 10 squares away from the mirror. That's twice as far as the focal point is. So, what color did I use for that? I used brown, didn't I? So this is the one. Again, if it comes off the arrowhead and is going in that direction, it'll never hit the mirror. But you have to imagine one that is coming, seems to be coming from here, but actually comes off of the arrowhead. See what I'm doing there? So it's heading towards the mirror, and then it reflects directly back on itself. So like, oh, I missed. Like that. Ignore that scribble there. Now, if this person sees that, that person's brain will just follow this line of sight directly back, and it'll be like, oh, there's the image back here somewhere. Now this drives some people crazy, but it's about in the same spot. They won't always perfectly coincide. There's a lot of sort of approximations that we're doing here. But right about the point where all of these are meeting or intersecting is that point we call the image. But I draw this image, not like I did the first one, but dashed. I think I'm going to put it about here. There's the arrowhead. I'm drawing it dashed, and I'm going to put the tail, again, right on the principal axis. That's that last rule that says we don't have to work to figure out where the tail is, because its image will always be on the principal axis since it's starting there. So what does this mean for our lost description? Well, the location is on the wrong side of the mirror, and the convention, since it's on the wrong side, it's considered a virtual image, and we use a negative sign on that. Okay, so the location is 1, 2, 3, about 3.5, but this time it's on the wrong side, or the virtual side, so that's negative 3.5. And if these are centimeters again, I'll just put the centimeters on. Now, what's the orientation? This time, it has not been flipped over. It's called upright. What is the size? We just measure, again, using these squares as a centimeter. 1, 2, 3, 4, 5, 6.5 or so. That's a positive number this time because it's not flipped over. The inverted images are the ones that had negative sizes or negative magnification. This has been magnified, notice. This is bigger than that. So sometimes some teachers just want you to tell that it's bigger. Okay, it's bigger by, I don't know, about 30% or so. I mean, the original one was 4 high, and this is about 6.5. So maybe about 50% magnification. And what is the type? Well, I described this already. This is called a virtual image. Again, much like a mirage, much like what we saw with the plane mirrors. Those are not things we could reach out and touch the image and put it on our hand. Okay. So, all right, that's the oddities when you have images where the points that reflect don't ever come together to a point. All right. So, all right, I'm going to leave it there. The next step in a different video is how you do the math of this. It's actually a lot quicker. We just have to know a couple equations and those sign conventions, and I'll take you through that on the next one. Okay. Let me know if you need help with this.